And welcome back as we continue our cosmic journey. Let's go ahead and take a look at the very beginning of the universe. So when we talk about the beginning of the universe, let's dial it all the way back to the very first few minutes of the universe's creation. Because we're talking about those first few minutes after the initial Big Bang. And three basic ideas really hold the key to tracing the change that occurred during the time just after the universe began. The first thing is that the universe cools as it expands. So in the first fraction of a second, the universe was unimaginably hot. After about 0.01 seconds, the temperature had dropped to about 100 billion Kelvin, and that's a pretty significant temperature. Now, granted, if we fast forward in time just a tiny bit, if we go about 3 minutes out, we'll see that that temperature has now fallen to 1 billion Kelvin, which is still about 70 times hotter than the interior of our sun. After a few 100,000 years, the temperature, of course, dropped even further, down to about 3,000 Kelvin, and has continued to cool since then. Now, the second step in understanding the evolution of the universe is to realize that in those very early times, the universe was so hot that it mostly contained just radiation, and not the matter that we see today. So things like even the basic elements like protons, neutrons, electrons. It was a very different world that we saw back then. What instead we see is a bunch of photons that fill the universe, and these would collide and produce material particles. Because under the conditions just after the Big Bang, energy could turn into matter, and matter, conversely, could also turn back into energy. Now, when we compare the universe today to what it was like right after the Big Bang, our universe is instead a relatively cold, hard time. The photons in the universe today typically have far less energy than the amount required to make new matter. So a lot of times when we look at our universe, all the matter that exists is all the matter that there will be. Our third key point is that the hotter the universe was, the more energetic the photons available to make matter and antimatter. So let's take a specific example. At a temperature of 6 billion Kelvin, a collision of two typical photons can create an electron and its antimatter counterpart, a positron. If the temperature exceeds 10 to the 14th Kelvin, much more massive protons and antiprotons can be created. And so if we kind of look at this visual representation of the time that has elapsed from the Big Bang, we can see here very early on, we don't necessarily have a good set of rules of how the universe functions. But as we start moving closer into the time elapsed since that Big Bang, we can start seeing things that are more familiar. Forces are unified, so that would be things like the strong and weak nuclear forces, the electromagnetic forces, gravity. Here we have radiation still dominating here at this point, though. It's not until you can start seeing we get down to these seconds that we see here. There are fractions of a second as we start moving into time getting closer and closer. We start seeing protons and antiprotons, then electrons and positrons. And finally, once we get into a large value here of seconds being whole, we start seeing atoms forming, and then eventually, once we get into closer toward today, we get much more familiar things such as stars and galaxies. Now, this is, of course, a scale that is, if you looked all the way down into fraction seconds, we get 10 to the negative 43rd, which is, of course, about as close to the start of the Big Bang as we can get. And, of course, we can see all the way up to 10 to the 17th, which is representing the number of seconds that has elapsed from the start of the Big Bang to today. And so if we look at the evolution of the universe, we can keep these three ideas in mind and actually trace the evolution of the universe from the time it was about 0.01 seconds old, and we had a temperature of about 100 billion Kelvin. But you might ask, why can't we start at the very beginning, like at time equals 0? Well, we don't really have any theories currently that allow us to penetrate time before 10 to the minus 43 second. As we just saw on that chart, that was the farthest left we could go. In fact, this time scale is already so small that we cannot relate anything to it in our everyday experience. And when the universe was that young, its density was so high that the general theory of relativity is not adequate to describe it. And even the concept of time starts to break down. By the time the universe was, of course, 0.01 seconds old, it consisted of a soup of matter and radiation. The matter, of course, include things like protons, neutrons, and leftovers from an even younger, hotter universe. And in this time, each particle collided rapidly with other particles because of the density. Now, the temperature was no longer high enough to allow colliding photons to produce neutrons or positrons, but it was sufficient to produce electrons and positrons. There's probably also a sea of exotic subatomic particles that would later play a role as dark matter. Now, at this time, of course, it was still too hot for protons and neutrons to combine to form the nuclei of atoms. Now, when the universe was a little more than 1 second old, the density had dropped to the point where neutrinos no longer interacted with matter, but simply travel freely through space. In fact, these neutrinos should still all be around us and have been traveling through space unimpeded and therefore unchanged since the universe was about 1 second old. And so measurements of their properties would actually offer us one of the best tests of the Big Bang model. Unfortunately, the fact that neutrinos interact so weakly with matter and that they've survived unaltered for all but the first second time is also the thing that kind of makes them very hard to be measured with our present techniques. And so if we go a little further out, we can see atomic nuclei form. Because when the universe was about 3 minutes old and its temperature was down to about 900 million Kelvin, protons and neutrons could then combine. At higher temperatures, these atomic nuclei had immediately been blasted apart by interactions with high energy protons and could not survive. But at the temperature and densities reached between the 3 and 4 minute mark after the beginning, deuterium, which is of course a proton and a neutron coming together, lasted long enough collisions could actually convert some of it into helium. In essence, the entire universe was acting very much the way the centers of stars do today, fusing new elements from simpler ones. In fact, we can even see a little bit of element 3, lithium, also forming during this time. By about 4 minutes after the Big Bang, helium was having trouble forming as the universe was still expanding and cooling down. And after the formation of helium and some lithium, the temperature dropped so low that the fusion of helium nuclei into still heavier elements could not occur. Now, no elements beyond lithium could form in the first few minutes. That 4-minute period was the end of the time when the entire universe was effectively a giant fusion factory. In the cool universe we know today, the fusion of new elements is limited to the center of stars and the explosions of supernovae. So we estimated that about 10 times more helium was generated in the first 4 minutes of the universe than in all the generations of stars. And if we take a look at this visual representation here, we can see, of course, just how some of that is going on. So at 10 to the minus 2 seconds, we can, of course, see gamma rays blasting together with photons. We got electrons and positrons coming up. And, of course, electrons and positrons can come back together to form more gamma rays. But by the 3-minute mark, we are now having protons and neutrons come together to form deuterium, which, of course, can form helium-3, and this gives a helium-4, which can, of course, come together from the deuterium to also make our helium-4 here, because we have a hydrogen-3 and a neutron floating around here. But by the time we're hitting that 300,000 to 700,000 year mark, you can see that things have very much stabilized with protons in the center with 1 electron. It turns out that all the deuterium, so a hydrogen nucleus with a neutron in it, in the universe was formed during the first 4 minutes. Now in stars, any region that is hot enough to fuse 2 protons to form a deuterium nucleus is also hot enough to change it further, either by destroying it through collision with energetic photons or by converting it into helium through nuclear reactions. So the amount of deuterium that can be produced in the first 4 minutes of creation depends on the density of the universe at the time the deuterium was formed. If the density were relatively high, nearly all the deuterium would have converted into helium through interactions with protons, just as it is in stars. If the density, though, was relatively low, then the universe would have expanded and thinned out rapidly enough that some of the deuterium could have survived. Now, the amount of deuterium we see today actually gives us a clue to the density of the universe when it was about 4 minutes old. Now, deuterium can only provide an estimate of the density of ordinary matter because the abundance of deuterium is determined by the particles that interact to form it, namely protons and neutrons alone. From the abundance of deuterium, we know that not enough protons and neutrons are present by a factor of about 20 to produce a critical density universe. We do know, though, that dark matter particles add to the overall matter density of the universe, which is then higher what is calculated for ordinary matter alone. And because dark matter particles do not affect the production of deuterium, the measurement of deuterium abundance cannot tell us how much dark matter exists.